Hello everyone, in this video I'm going to talk about liquid foundational models or liquid neural networks. I'm going to talk about how they are started, what is the inspiration behind them, what is the advantage of using them compared to in fact classical neural networks, and then in the second part of the video I'm going to talk about and we'll code together the whole liquid neural net, or let's call it liquid foundational model, the second version. So yes, let's just start and see what are they and how they technically started. So the thing is, liquid neural networks are a kind of new brain inspired neural network design, and they design to be kind of more adaptive and efficient than the traditional neural networks. So the thing is, unlike standard models and networks, which are kind of, they have a fixed operations for processing the input, the LNNs or liquid neural networks use differential equations, and this is the very important, in fact, part and the heart, I would say, heart of liquid neural networks. They use differential equations to describe how a neuron's state changes over time based on both the input and the current state of it. So this allows the network to behave more like a dynamic system. And if you honestly, if you think about it, that's technically how we humans think and the way that our brain works. So technically, for example, if I ask you what is your name, you might spend almost no time and reply immediately and tell me your name. But if I ask a very complex math problem, you're gonna spend some time over it and think about it and reason about it and then answer to me, which technically is that dynamic of the system, which you need to spend more time based on the input and based on the state of the your brain or the question or so on and so forth. So yeah, just like how neurons in the human brain react and adapt to new stimuli. So the key innovation is that each neuron in an liquid neural net has a time varying, this part is also very important, has a time varying input dependent liquid state, which makes the network naturally better at handling time series, for example, like sensor data, or I don't know, weather forecasting, so on and so forth. Anything that has a changing factor in the environment. And because of this dynamic nature, LNNs are specifically good at tasks where, as I mentioned, they are timed, and timing and adaptability are important, such as robotics again, I don't know, reinforcement learning, or anything, as I mentioned, including time or real world even sensors. So even despite having the fewer parameters than the classical and traditional models, LLNs are often perform better on these kind of tasks. And also, when we say time dependent, remember that text and the sequence of text could be seen as a kind of time dependent data. So there could be good LLMs out of it, which if you go to Hugging Face and search for it, you will find some of their liquid, in fact, LLMs. So yeah, that's technically what they are and how it started. And by the way, this work generally is based on uh, a researcher and a research group in MIT University, which I think led by Ramin Hassani, and right now they have the company called Liquid, and they're making their own foundational models, which you can, as I mentioned, you can go to Hugging Face and check out those LLMs, and they have vision models and voice models right now, which when I tried them, they work pretty well, despite the fact that they don't have that many parameters, which is really nice, I would say. I can say it could be a leading, maybe a leading architecture or models for edge devices. I would say it looks very promising for that kind of use case. So, as I mentioned, in the traditional neural networks, data will be processed in a fixed, rigid manner, but the world is dynamic, and these liquid neural networks try to adapt the time and do it in a kind of change the process and processing time based on the input and their internal state, which has been depicted in these two in fact graphs, which I'm gonna go in a moment. I'm gonna go into more details of it and how this technically happens, because you know that it's a little bit hard to use differential equations in neural networks, but it would be really fun to see how that exactly happens. And also, the other kind of innovation I would say is in a standard hybrid transformers, we know that data will go through the pipeline, through the whole model in a sequential manner. But again, if you think about it, that's technically not how we humans think or behave. We might spend, it's not the same pipeline, it's not the same way of thinking for everything. We change the way we think based on the problem, based on the task. It could be vision task, it could be speaking, so on and so forth. So here in liquid one, as you can see, the connections are not necessarily back to back. You can go, I don't know, 10 steps forward, come back, go one step or two steps sequentially, and then come back and go, I don't know, 10 steps forward, so on and so forth. So you can manage the time. So that's the important part of it, I would say. Just quickly, we're gonna go through the architecture of it and see how it works, and then we're gonna start coding it. So as you can see, this is a very high level architecture of the LFM2, Liquid Foundation Model 2, which is one of those one of the LLMs. And as you can see, so what we have the input token IDs, then we have token embeddings, then we have convolutional blocks, we have 10 conv blocks here, and right after that, and I'm gonna explain in a moment what these LFM2 conv blocks are exactly, and right after these conv blocks we have 6 attention or transformer, or maybe let's say liquid transformer blocks, and right after that we have RMS norm, and then we have the hidden state, and so on and so forth. Vocab size is configurable, hidden size is H, conv blocks 10, attention block 6, normalization type is RMS norm, and positional encoding is rotary positional encoding. And here we have LFM2 transformer block, which we have the input, and then right after the input we have RMS norm, and then group query attention to make it somehow more optimize the calculation. Then we have the residual networks, residual connections, and right after that we have again another RMS norm layer. We have Suiklu feed forward, which is technically switch gated linear unit, and we're gonna go once we go to the code, I'm gonna explain how it looks like, and we're gonna code this part and every other part in full detail. Don't worry about them. And then again another residual connection, and then we have the output. So this was technically the LFM2 transformer block, but how about the LFM2 convolutional block, which we had right here? And this part is somehow, I would say, an important part, because what we said here was that, okay, we have a time kind of liquidity modularity, but how that happens and how we can kind of decide how much time based on the input and the state, internal state, we want to spend on each of the for each input type. So the thing is, it's not exactly um, the differential equation or anything like that, but how this dynamic behavior works in LFM2. In the LFM2 conv block, there are two main gating steps, as you can see here, gate B and gate C. These gates are essentially learned parameters that depend on the input itself. So instead of having a fixed weight, this is very important, instead of having a fixed weight that always multiplies the input in the same way, the network learns a gate that changes based on what the input is, which is very important. So the first gate, gate B over here, when you feed an input tensor, let's say X, into the block, it goes through a linear layer that processes three sets of, in fact, it goes through this linear layer, divides it into three, or copies that into three, let's say, values, and then one of them goes to the gate B, the first gate. We have the gate C over here, and then one for the main transformer input projects. And then the input is multiplied by the first gate. This means technically the input is dynamically scaled by B over here, which depends on the input itself. So it kind of decides, and it can change itself based on how the input looks like, so on and so forth. And then we have convolution and second gating, gate C over here, convolution and the gate C. So what happens there, after the scaling, the data goes through a convolutional layer, which gives it a kind of local context sensitivity, which is very important. After the convolution, the input is again scaled by the second gate C over here. And why this is like a liquid behavior in a traditional neural network? Because in a traditional neural network, the transformation is fixed once training is done. But here, because the gate B and gate C are learned functions of the input, the network can adapt its internal time constants and its internal behavior based on what it sees. In other words, I can say that the network can become more flexible and kind of context sensitive, much like a liquid neural network, even though it's implemented in a discrete convolutional format. And then after that, we have the dropout and linear layer again to scale or whatever, and then the output. And the last one, which is group query attention. Again, we have, I don't know, q, k value. After that, for the q and k, we were gonna reshape it based on how many heads we want to have. And then we do the rotary positional encoding for both of them. And by the way, this arc might be a little bit misleading. We're not gonna feed the data from this line into this line. This means that we're gonna apply rotary positional encoding for these both sides of the data, and then just again repeat k and v for the kv cache or something like that, and then we're gonna do a simple scale dot product w output time multiplying that by the weight of the output, and then we have the output. And yeah, so I think it should be done here. I think I covered almost everything, but yeah, Now let's go to the coding part and see. We're gonna start from literally each of these blocks, and we're gonna code and go through each of these blocks and see how they look like and how exactly you can define and design and code LFM2 from scratch.